Software Quality Assurance (SQA). In this video, we are going to see about Software Quality Assurance (SQA). Software Quality Assurance (SQA). Definition: SQA is a collection of activities during software development that focus on increasing the quality of the software being produced. Umbrella activity applied throughout the software process. Responsibility of many stakeholders, that is software engineers, project managers, customers, salespeople, SQA group. Quality assurance elements. Standards. Reviews and audits. Testing. Error or defect collection and analysis. Change management. Education. Vendor management. Security management. Safety. Risk management. Task of Software Quality Assurance (SQA). The tasks of SQA are: prepare SQA plan for the project, participate in the development of the project software process description, review software engineering activities to verify compliance with the defined software process, audit designated software or products to verify compliance with those defined as part of the software process, record any evidence of non-compliance and report them to management. Activities of Software Quality Assurance. Application of technical methods. Tools to aid in the production of a high-quality specification, that is, specification checkers and verifiers. Tools to aid in the production of high-quality designs, that is, design browsers, checkers, cross-references, verifiers. Tools to analyze source code for quality. Formal technical reviews. Group analysis of specification or design to discover errors. Software testing. Enforcement of standards. Specification and design standards. Implementation standards. Documentation standards. Control of change. Format management of change. Changes require formal request to approve authority. Approving authority makes decision on which changes get implemented. Programmers are not permitted to make unapproved changes to the software. Opportunity to evaluate the impact and cost of changes before committing resources. Evaluate effect of proposed changes on software quality. Measurement. Ongoing assessment of software quality. Track quality changes as system evolves. Warn management if software quality appears to be degrading. Record keeping and reporting. Collect output and reports of SQA activities. Disseminate reports to software managers. Maintain archive of SQA reports. Maintain log of software development activity to satisfy legal requirements. maintain institutional memory of the software development effort. Debugging. In this video, we are going to see about debugging. Debugging is the process of removal of a defect. It occurs as a consequence of successful testing. Debugging process starts with execution of test cases. The actual test results are compared with the expected results. The debugging process attempts to find the lack of correspondence between actual and expected results. The suspected causes are identified and additional tests or regression tests are performed to make the system to work as per requirement. Common approaches in debugging: brute force method. The memory dumps and runtime traces are examined and program with right statements is loaded to obtain clues to error causes. In this method, let computer find the error approach is used. This is the least efficient method of debugging. Backtracking method. This method is applicable to small programs. In this method, the source code is examined by looking backwards from symptom to potential causes of errors. Causes elimination method. This method uses binary partitioning to reduce the number of locations where errors can exist. Thus, testing is an essential activity carried out during software development process for improving quality of the product. Program slicing. This technique is similar to backtracking. The search space is reduced by defining slices. A slice program for a particular variable and a particular statement is a set of source lines preceding this statement that can influence the value of that variable. Program slicing makes use of the fact that an error in the value of that variable can be caused by the statements on which it is data dependent. Debugging guidelines. In this video, we are going to see about debugging guidelines. Debugging is often carried out by programmers based on their ingenuity and experience. The following are some general guidelines for effective debugging. Many times, debugging requires a thorough understanding of the program design. Trying to debug based on a partial understanding of the program design may require an inordinate amount of effort to be put into debugging even for simple problems. Debugging may sometimes even require full redesign of the system. In such cases, a common mistake that novice programmers often make is attempting not to fix the error but its symptoms. One must be aware of the possibility that an error correction may introduce new errors. Therefore, after every round of error fixing, regression testing must be carried out. Debugging detection strategies. As debugging is a difficult and time-consuming task, it is essential to develop a proper debugging strategy. This strategy helps in performing the process of debugging easily and efficiently. This strategy is a disciplined thought process where errors can be debugged by moving outwards from the particulars to the whole. To perform an indexion strategy, a number of steps are followed, which are listed below. Locating relevant data. All the information about a program is collected to identify the functions which are executed correctly and incorrectly. Organizing data. The collected data is organized according to importance. The data can consist of possible symptoms of errors, their location in the program, the time at which the symptoms occur during the execution of the program, and the effect of these symptoms on the program. Devising hypothesis. The relationships among the symptoms are studied and a hypothesis is devised that provides the hints about the possible causes of errors. Proving hypothesis. In the final step, the hypothesis needs to be proved. It is done by comparing the data in the hypothesis with the original data to ensure that the hypothesis explains the existence of hints completely. In case the hypothesis is unable to explain the existence of hints, it is either incomplete or contains multiple errors in it. Detection strategies. In this strategy, first step is to identify all the possible causes, and then using the data, each cause is analyzed and eliminated if it is found invalid. Note that as an induction strategy, deduction strategy is also based on some assumptions. To use this strategy, the steps followed are: identifying the possible causes or hypothesis. A list of all the possible causes of errors is formed. Using this list, the available data can be easily structured and analyzed. Eliminating possible causes using the data. The list is examined to recognize the most probable cause of errors, and the rest of the causes are deleted. Refining the hypothesis. By analyzing the possible causes one by one and looking for contradiction leads to elimination of invalid causes. This results in a refined hypothesis containing few specific possible causes. Reliability analysis. In this video, we are going to see about reliability analysis. Software must satisfy non-functional requirements (NFRs). Reliability is one of these NFRs. In software engineering, software reliability is a probability of failure-free operation of a software system for a specified period of time in a computer environment. Many researchers propose the reliability analysis method. These are based on Markov chain or Petri nets or other methods. These approaches have some limitations. One of these limitations is that the current reliability analysis methods do not support traceability. UML-based reliability analysis. UML-based reliability analysis method is one of these reliability analysis approach. UML is widely used in software modeling. UML can be modeled with reliability analysis. Software can be tested after development phase. Many UML-based approach can provide analysis capability in design phase. Proposed approach. We propose a reliability prediction model with a traceability based on UML. This approach is to build software reliability prediction model. This model can be transformed to Software Reliability Prediction Model, SRPM. SRPM can analyze software reliability and support traceability of the reliability. Software Reliability Model. Software Reliability Model is based on UML such as use case diagram, sequence diagram, activity diagram, class diagram. Use case diagram. Use case diagram represent usages of the software. It can represent how many each scenario is used. Sequence diagram. It can represent scenarios for each use case. This diagram has the number of method call in each sequence and method name and an order of method call. Class diagram. Class diagram can represent classes, methods, and attributes. In this diagram, reliability-related attributes such as MTTR and MTTF can be described with some annotations. Activity diagram. Activity diagram can represent operations for each method. It contains flow of each method. Complexity analysis. In this video, we are going to see about complexity analysis. The term complexity stands for state of events or things which have multiple interconnected links and highly complicated structures. In software programming, as the design of software is realized, the number of elements and their interconnections gradually emerge to be huge, which becomes too difficult to understand at once. Software design complexity is difficult to assess without using complexity metrics and measures. Halstead's complexity measures. Halstead's metrics depends upon the actual implementation of program and its measures, which are computed directly from the operators and operands from source code in static manner. A computer program is an implementation of an algorithm considered to be a collection of tokens which can be classified as either operators or operands. Various indicators to check complexity of module is shown in the table. When we select source file to view its complexity details in metric viewer, the following result is seen in metric report. Guideline for calculating operands and operators. All the variable and constants are considered as operands. Local variables with same name, if occurring in different functions, are counted as unique operand. Function calls are considered as operators. The looping statements do while, for are operators. The statements if else are operators. The switch case statements are considered as operators. The reserve words, return, default, continue, break, size of are all operators. The brackets, commas, semicolons are operators. The unary and binary operators are considered as operators. All hash directives can be ignored. Comments are not considered. Complexity measures. In this video, we are going to see about complexity measures. Cyclomatic complexity measures. Definition. Cyclomatic complexity is a software metric that gives a quantitative measure of logical complexity of the program. It defines the number of independent paths in the basis set of the program that provides the upper bound for the number of tests that must be conducted to ensure that all the statements have been executed at least once. 3 methods of computing cyclomatic complexities. Method 1. The total number of regions in the flow graph is a cyclomatic complexity. Method 2. The cyclomatic complexity V of G for a flow graph G can be defined as V of G is equal to E minus n plus 2, where E is the total number of edges in the flow graph, n is the total number of nodes in the flow graph. Method 3. The cyclomatic complexity V of G for a flow graph G can be defined as V of G is equal to P plus 1. Consider following code fragment with line numbered. The cyclomatic complexity of the above module is function point. In this video, we are going to see about function point. It is widely used to measure the size of software. Function point concentrates on functionality provided by the system. Features and functionality of the system are used to measure the software complexity. Function point counts on 5 parameters named as external input, external output, logical internal files, external interface files, and external inquiry. To consider the complexity of software, each parameter is further categorized as simple, average, or complex. Parameters of function point. External input. Every unique input to the system from outside is considered as external input. Uniqueness of input is measured as no two inputs should have same formats. These inputs can either be data or control parameters. Simple, if input count is low and affects less internal files. Complex, if input count is high and affects more internal files. Average, in between simple and complex. External output. All output types provided by the system are counted in this category. Output is considered unique if their output format and or processing are unique. Simple, if output count is low. Complex, if output count is high. Average, in between simple and complex. Logical internal files. Every software system maintains internal files in order to maintain its functional information and to function properly. These files hold logical data of the system. This logical data may contain both functional data and control data. Simple, if number of record types are low. Complex, if number of record types are high. Average, in between simple and complex. External interface files. Software system may need to share its files with some external software, or it may need to pass a file for processing or as parameter to some function. All these files are counted as external interface files. External inquiry. An inquiry is a combination of input and output where users send some data to inquire about as input and the system responds to the user with the output of the inquiry processed. The complexity of a query is more than external input and external output. Query is said to be unique if its input and output are unique in terms of format and data. Simple, if query needs low processing and yields small amount of output data. Complex, if query needs high process and yields large amount of output data. Average, in between simple and complex. Each of these parameters in the system is given weightage according to their class and complexity. The table below mentions the weightage given to each parameter. Parameter: simple, average, complex. Inputs: 3, 4, 6. Outputs 4, 5, 7. Inquiry 3, 4, 6. Files 7, 10, 15. Interfaces 5, 7, 10. These function points are adjusted according to their environment complexity. Software quality. In this video, we are going to see about software quality. The quality of a product is defined in terms of its fitness of purpose. That is, a good quality product is exactly what the users want it to do. Since for almost every product, fitness of purpose is interpreted in terms of satisfaction of the requirements laid down in the SRS documents. The modern view of the quality associates with the software products several quality factors such as the following. Portability. A software product is said to be portable if it can be easily made to work in different hardware and operating system environments and easily interface with external hardware devices and software products. Usability. A software product has good usability if different categories of users can easily invoke the functions of the product. Reusability. A software product has good reusability if different modules of product can easily be reused to develop new products. Correctness. A software product is correct if different requirements as specified in the SRS document have been correctly implemented. Maintainability. A software product is maintainable if errors can be easily corrected as and when they show up, new functions can be easily added to the product, and the functionalities of the product can be easily modified, etc. McCall's quality factors. McCall's distinguishes two levels of quality attributes. The higher level attributes known as quality factor or external attributes can only be measured indirectly. The second level quality attributes are called quality criteria, can be measured directly either objectively or subjectively. By combining the rating of several criteria, we can either obtain a rating for the quality factors or the extent to which they are satisfied. Example, the reliability cannot be measured directly but by measuring the number of defects encountered over a period of time. Thus, reliability is a higher level quality factor and the number of defects is a lower level quality factor. ISO 9126. ISO 9126 defines a set of hierarchical quality characteristics. Each subcharacteristic in this is related to exactly one quality characteristic. This is in contrast to the McCall's quality attributes that are heavily interrelated. Another difference is that the ISO characteristic strictly refers to a software product, whereas McCall's attributes capture process quality issues as well. What are software metrics? Tools for anyone involved in software engineering to understand varying aspects of the code base and the project progress. They are different from just testing for errors because they can provide a wider variety of information about the following aspects of software systems. Quality of the software. Different metrics look at different aspects of quality, but this aspect deals with the code. Schedule of the software project on the whole, that is, some metrics look at functionality and some look at documents produced. Cost of the software project includes maintenance, research, and typical costs associated with a project. Size or complexity of the software system. This can be either based on the code or at the macro level of the project and its dependency on other projects. Scope of software metrics. In this video, we are going to see about scope of software metrics. Productivity models and measures. The pressing needs of management have also resulted in numerous attempts to define measures and models for assessing staff productivity during different software processing and in different environments. It shows productivity as a function of value and cost. Each is then decomposed into other aspects expressed in measurable form. This model is significantly more comprehensive view of productivity than the traditional one, which simply divides size by effort. This is many managers make decisions based on the rate at which the lines of codes are being written per person month of effort. This simpler measure can be misleading, if not dangerous. Data collection. The quality of any measurement program is clearly dependent on collection, but collecting data is easier said than done, especially when data must be collected across a diverse set of projects. Thus, data collection is becoming a discipline in itself. Specialists work to ensure that measures are defined unambiguously, that collection is consistent and complete. The data integrity is not at risk, but it is acknowledged that metrics data collection must be planned and executed in a careful and sensitive manner. The figure shows that contains several examples of how the data collected can be distributed into simple charts and graphs that show managers the progress and problems of development. Data collection is also essential for scientific investigation of relationships and trends. Quality models and measures. Productivity cannot be viewed in isolation without accompanying assessment of product quality. Speed of production is meaningless. This observation has led software engineers to develop models of quality whose measurements can be combined with those of productivity models. Example: Boehm's advanced COCOMO cost estimation model is tied to quality model. Similarly, the McCall's quality model, commonly called FCM, that is Factor Criteria Metric Model, is related to productivity. These models are usually constructed in a tree-like fashion. The upper branches hold important high-level quality factors of software products such as reliability and usability that we would like to quality. Each quality factor is composed of lower-level criteria such as structuredness and traceability. The criteria are easier to understand and measure than the factors, thus actual measures are proposed for the criteria. The tree describes the pertinent relationships between factors and their dependent data, so we can measure in terms of the dependent criteria measures. Reliability models. Most quality models include reliability as a component factor, but the need to predict and measure reliability itself has led to a separate specialization in reliability modeling and prediction. Littlewoods and others provide a rigorous and successful examples of how a focus on an important product quality attributes has led to increased understanding and control of our products. Structural and complex metrics. Desirable quality attributes like reliability and maintainability cannot be measured until some operational version of the code is available. Yet, we wish to be able to predict which parts of the software system are likely to be less reliable, more difficult to test, or require more maintenance than others, even before the system is complete. As a result, we measure structural attributes of representations of the software which are available in advance of execution. Then we try to establish empirically predictive theories to support quality assurance, quality control, and quality prediction. Management by metrics. Measurement is becoming an important part of the software project management. Customers and developers rely on measurement-based charts and graphs to help them decide if the project is on track. Many companies and organizations define a standard set of measurements and reporting methods so that projects can be compared and contrasted. This uniform collection and reporting is especially important when software plays a supporting role in the overall project. Evaluation of methods and tools. Many articles and books describe new methods and tools that may make your organization or project more productive and your products better and cheaper. But it is difficult to separate the claims from the reality. Many organizations perform experiments, run case studies, or administer surveys to help them decide whether a method or tool is likely to make a positive difference in their particular situations. These investigations cannot be done without careful, controlled measurement and analysis. Limitation. There is a strong tendency for professionals to display over-optimism and overconfidence. Arguments that simplistic measurements may cause more harm than good, that is, data that is shown because it is easier to gather and display. There are arguments about the effects that software metrics have on the developer's productivity and well-being. Quality control QC. In this video, we are going to see about quality control QC. Define quality control QC. Quality control QC is a procedure or set of procedures intended to ensure that a manufactured product or performed service adheres to a defined set of quality criteria or meets the requirements of the client or customer. QC is similar to, but not identical with, quality assurance QA. Quality assurance QA. QA is defined as a procedure or set of procedures intended to ensure that a product or service under development, that is before work is complete as opposed to afterwards, meets specified requirements. QA is sometimes expressed together with QC as a single expression, quality assurance and control, that is QA, QC. In order to implement an effective QC program, an enterprise must first decide which specific standards the product or service must meet. Then the extent of QC actions must be determined. For example, the percentage of units to be tested from each lot. Next, real-world data must be collected. For example, the percentage of units that fail and the results reported to management personnel. After this, corrective action must be decided upon and taken. For example, defective units must be repaired or rejected and poor service repeated at no charge until the customer is satisfied. If too many unit failures or instances of poor service occur, a plan must be devised to improve the production or service process, and then that plan must be put into action. Finally, the QC process must be ongoing to ensure that remedial efforts, if required, have produced satisfactory results and to immediately detect recurrences or new instances of trouble. Types of control. Quality control techniques can be classified by their purpose. Preventive quality control. Do it right. Preventive methods avoid defects by setting standards for processes, products, and resources. The choices are derived from sound software engineering principles and from past experiences with similar systems within the same organization or similar organizations that have demonstrated which techniques lead to higher quality products and which factors cause defects. Standards may be processed to follow quantities of any qualifications for resources and normal values for what results to expect, such as density of errors found in testing and productivity during coding. Detective quality control techniques. Find deficiencies and fix them. Detective techniques look for deficiencies in products, processes, and resources. These techniques assess the quality of the intermediate products and look for defects that must be corrected. Some detective techniques analyze the causes of defects in the processes and resources used to produce products. These analyses can lead to corrective actions that are preventive for the remainder of that development or the future developments. Effect of quality control parameters. The TSQC model states that quality is achieved by regulating the quality control parameters. Therefore, the relationship between the quality control techniques and the products, processes, and resources they can affect helps determine the relevance of a technique, especially when the parameter type causing defects has been identified and corrections are needed. Quality control issues and techniques. In this video, we are going to see about quality control issues and techniques. What are the quality requirements for the final product? Quality requirements include operational requirements such as usability and survivability, as well as implementation quality such as maintainability. Not only must the quality requirements be stated, but they must be stated well. Operations concept document. One of the most important ways to define requirements is through an operations concept document that describes how the system will be used. It is a description of the dynamics of its use and how use changes over time. This view is necessary when establishing quality requirements and prioritizing them. Sometimes an operation concept document does not exist at the time a system development begins, and its lack adversely affects the quality of the system. RFR preparation and review. The system-level requirements are usually contained in the system or subsystem specification, which is part of the RFP package. This is the place where the quality requirements should be defined. A comprehensive review should be done prior to its release to assure that the requirements are clearly and completely defined and are verifiable. Process and quality. A process is a transformation of a set of inputs into outputs that satisfy customer needs and expectations in the form of products, information, or services. Everything we do is a process. So in each area or function of an organization, there will be many processes taking place. Example, a finance department may be engaged in budgeting processes, accounting processes, salary and wage processes, etc. Each process in each department or area can be analyzed by an examination of the inputs and outputs. Clearly, to produce an output that meets the requirements of the customer, it is necessary to define, monitor, and control the inputs to the process, which in turn may be supplied as output from an earlier process. At every supplier or customer interface, there resides a transformation process, and every single task throughout an organization must be viewed as a process in this way. In every organization, there are some very large processes, groups of smaller processes often called core business processes. These are activities that the organization must carry out especially well if its mission and objectives are to be achieved. It is crucial if the management of quality is to be integrated into the strategy for the organization. The control of quality can only take place at the point of operation or production, where the letter is word processed, the sales call made, the patient admired, or the chemical manufactured. The act of inspection is not quality control. When the answer to "have we done the job correctly" is given indirectly by answering the questions of capability and control, then we have assured quality, and the activity of checking becomes one of quality assurance, making sure that the product or service represents the output for an effective system to ensure capability and control. It is frequently found that organizational barriers between functional or departmental employers encouraged the development of testing and checking of services or products in a vacuum without interaction with other departments. Process or system. Objectives. Statistical quality control (SQC). Build in the control limits of a process that spots and identifies causes of variations. Statistical process control (SPC). Provide information on how productivity and quality can be continuously improved through problem identification. Just-in-time (JIT). Reduce inventory cost, production time, and space requirements. Computer Integrated Manufacturing (CIM). Lower cost, shorten lead time, and improve quality based on information sharing by linking management and financial information systems, departmental computing, process management systems, and factory systems for controlling machinery and manufacturing processes. Quality function deployment. Integrate the three dimensions of company-wide quality, focus on customer requirements, translation of quality perceptions into product characteristics and then into the manufacturing process. Benefits of quality control. Encourages quality consciousness. The most important advantage derived by introducing quality control is that it develops and encourages quality consciousness among the workers in the factory, which is greatly helpful in achieving desired level of quality in the product. Reduction in production cost. By undertaking effective inspection and control over production processes and operations, production costs are considerably reduced. Quality control further checks the production of inferior products and wastages, thereby bringing down the cost of production considerably. Most effective utilization of resources. Quality control ensures maximum utilization of available resources, thereby minimizing wastage and inefficiency of every kind. Improved techniques and methods of production. By supplying technical and engineering data for the product and manufacturing processes, improved methods and designs of production are ensured by quality control. Increased goodwill. By producing better quality products and satisfying customers' needs, quality control raises the goodwill of the concern in the minds of people. A reputed concern can easily raise finances from the market. Approaches to software quality assurance. In this video, we are going to see about approaches to software quality assurance. Software quality assurance is an umbrella activity that is applied throughout the software process. The first formal quality assurance and control function was introduced at Bell Labs in 1916. In a multi-testing strategy is drawn. Formal technical reviews that are applied throughout the software process. SQA goals. The major goals of SQA are as follows. SQA activities are planned. Non-compliance issues that cannot be resolved within the software project are addressed by senior management. Adherence of software products and activities to the applicable standards, procedures, and requirements is verified objectively. Affected groups and individuals are informed of SQA activities and results. SQA plan. The SQA plan defines the activities performed to provide assurance that the software-related items delivered to the customer conform to the established and contracted technical requirements. The SQA plan also describes how the project will be audited to ensure that the policies, standards, practices, procedures, and processes applicable to the project are followed. Software quality assurance is a plan that defines the quality processes and procedures that should be used. This involves selecting and instantiating standards for products and processes and defining the required quality attributes of the system. The SQA plan provides a roadmap for instituting software quality assurance developed by the SQA group. The plan serves as a template for SQA activities that are instituted for each software project. The quality plan should select those organizational standards that are appropriate to a particular product and development process. New standards may have to be defined if the project uses new methods and tools. An outline structure for a quality plan includes product introduction, a description of the product, its intended market, and the quality expectation for the product. Product plans, the critical release dates and responsibilities for the product along with plans for distribution and product servicing. Process descriptions, the development and service processes that should be used for product development and management. Quality goals, the quality goals and plans for the product including an identification and justification of critical product quality attributes. Risk and risk management, the key risks that might affect product quality and the actions to address these risks. Preparation of a software quality assurance plan for each software project is a primary responsibility of the software quality assurance group. Topics in a software quality assurance plan include purpose, scope of plan, list of references to other documents, management, including organization, tasks, and responsibilities. Review software engineering activities to verify compliance with the defined software process. Audit designated software work products to verify compliance with those defined as part of the software product. Ensure that any deviations in software or work products are documented and handled according to a documented procedure. Record any evidence of non-compliance and report them to management. Coordinates and control change. Helps collect and analyze metrics. Formal approaches to SQA. In this video, we are going to see about formal approaches to SQA. Software engineering commonly has argued that SQA requires a more formal approach. It can be argued that a computer program is a mathematical object. System and semantics can be defined for every programming language. Formal approaches for software requirements are also available. If requirement specification and programming language can be represented in a rigorous manner, that it should be possible to apply mathematical proof of correctness to show that program conforms exactly to its specification, which is SQA. Proof of correctness. Proof of correctness is used to demonstrate that a program conforms exactly to its specifications. A proof of correctness is a mathematical proof that a computer program or a part thereof will, when executed, yield correct results, that is, results fulfilling specific requirements. Before proving a program correct, the theorem to be proved must, of course, be formulated. Hypothesis. The hypothesis of such a correctness theorem is typically a condition that the relevant program variables must satisfy immediately before the program is executed. The condition is called precondition. Thesis. The thesis of the correctness theorem is typically a condition that the relevant program variables must satisfy immediately after execution of the program. This latter condition is called the post-condition. Developed with a language with a rigorous syntax. Statistical quality assurance. Information about software defects is collected and categorized. An attempt is made to trace each defect to its underlying cause, for example, not conforming to the specification, design error, violation of standards, poor communication with customer, and so on. Using the Pareto principle, that is 80% of defects can be traced to 20% of all possible causes. Isolate the 20% causes, that is a vital few. Once a vital few causes have been identified, correct the problems that have caused the defects. The clean room process. Use statistical quality control and formal program verification. An attempt to prevent defects rather than find defects. In projects attempted so far with this method, has not been widely applied in industry. Requires significant changes in both management and technical approaches to software development. Reliability. In this video, we are going to see about reliability. The reliability of a software product essentially denotes its trustworthiness or dependability. defined as the probability of failure-free operation of a computer program in a specified environment for a specified time period. Measures of reliability. Mean time between failure, that is MTBF, is equal to MTTF plus MTTR. MTTF is mean time to failure. MTTR is mean time to repair. Availability, MTTF by MTTF plus MTTR into 100%. We can summarize the main reasons that make software reliability more difficult to measure than hardware reliability. The reliability improvement due to fixing a single bug depends on where the bug is located in the code. The perceived reliability of a software product is observed dependent. The reliability of a product keeps changing as errors are detected and fixed. Hardware versus software reliability. Hardware reliability. Software reliability. Hardware components fail mostly due to wear and tear. Software components fail due to bugs. In hardware reliability, in the first phase of the manufacturing, there may be a high number of faults, but after discovering and removing faults, this number may decrease, and gradually in the second phase, that is useful life, there exists only a few number of faults. After this phase, there will be wear out phase in which the physical component wear out due to the time and usage, and the number of faults will again increase. But in software reliability, at first phase, that is while testing and integration, there will be high number of faults, but after removing the faults, there exists only a few number of faults, and this process of removing the faults continues at a slower rate. Software products will not wear out with time and usage, but may become outmoded at a later stage. A logic gate may be stuck at 1 or 0, or resistor might short circuit. To fix the hardware fault, one has to either replace or repair the failed part. A software product would continue to fail until the error is tracked down and either the design or the code is changed to fix the bug. Reliability metrics of software product. In this video, we are going to see about reliability metrics of software products. The reliability requirements for different categories of software products may be different. For this reason, it is necessary that the level of reliability required for a software product should be specified in the software requirement specification SRS documents. A good reliability measure should be observer independent so that different people can agree on the degree of reliability of a system. In absence of such measures, we discuss 6 metrics that correlate with reliability as follows. Rate of occurrence of failure, ROCOF. ROCOF measures the frequency of occurrence of failures. ROCOF measures of software product can be obtained by observing the behavior of a software product in operation over a specified time interval and then calculating the ROCOF value as a ratio of the total number of failures observed and duration of observation. Example, library software is idle until a book issue request is made. Therefore, for a typical software product such as payroll software, applicability of ROCOF is very limited. Mean time to failure, MTTF. MTTF is the time between 2 successive failures averaged over a large number of failures. To measure MTTF, we can record the failure data for n failures. Let the failures occur at the time instance T1, T2, T3 and so on up to Tn. Mean time to repair MTTR. Once failure occurs, some time is required to fix the error. MTTR measures the average time it takes to track the error causing the failure and to fix them. Mean time between failure, MTBF. The MTTF and MTTR metrics can be combined to get the MTBF metric. MTBF is equal to MTTF plus MTTR. Thus, MTBF of 300 hours indicates that once a failure occurs, the next failure is expected after 300 hours. In this case, the time measurements are real time and not the execution time as in MTTF. Probability of failure on demand, POFOD. Unlike the other metrics discussed, this metric does not explicitly involve time measurements. POFOD measures the likelihood of the system failing when a service request is made. Availability. Availability of a system is a measure of how likely would the system be available for use over a given period of time. This metric not only considers the number of failures occurring during a time interval, but also takes into account the repair time of a system when a failure occurs. ISO 9000. In this video, we are going to see about ISO 9000. International Standards Organization ISO is a consortium of 63 countries established to formulate and foster standardization. ISO published its 9000 series of standards in 1987. ISO registration. The effort required to obtain ISO 9000 registration varies directly with how closely an organization's process fits the ISO 9000 model. ISO 9000 registration is granted when an accredited inspection organization certifies that the organization practices conform to the ISO standard. Re-registration is required for every 3 years and surveillance audits are performed every 6 months. ISO registration can cost a lot of time, effort and money to achieve. It requires continuing effort to stay registered. A cyclic view of ISO 9000 registration. ISO 9000 certification focuses on how well the processes are documented, not on the quality of the process. Many companies do the minimum required to achieve ISO 9000 certification for business reasons, but forget about it as soon as the ISO 9000 inspectors have signed off. ISO 9000 forces companies to act in a way which make the things worse for their customers. ISO 9000 is based on the faulty premise that work is best controlled by specifying and controlling procedures. Your product and the processes used to produce it can be absolutely terrible, but you can get ISO 9000 certification as long as the processes are well documented. ISO 9000 for software industry. In this video, we are going to see about ISO 9000 for software industry. ISO 9000 is a generic standard that is applicable to a large gamut of industries, starting from a steel industry to a service rendering company. Therefore, many of the classes of the ISO 9000 documents are written using generic terminologies, and it is very difficult to interpret them in the context of software development organizations. Two major differences between software development and development of other kinds of products are as follows. Software development, other development. Software is intangible and therefore difficult to control. It means that software would not be visible to the user until the development is complete and the software is up and running. It is difficult to control and manage anything that you cannot see and feel. In contrast, any other type of product manufacturing such as core manufacturing, you can see a product being developed through various stages such as fitting engine, fitting doors, etc. It becomes easy to accurately determine how much work has been completed and to estimate how much more till will it take. During software development, the only raw material consumed is data. Large quantities of raw materials are consumed during the development of any other product. Due to such radical differences between software and other type of product development, it was difficult to interpret various clauses of the original ISO standard in the context of software industry. Therefore, ISO released a separate document called ISO 9000 Part 3 in 1991 to help interpret the ISO standard for software industry. At present, official guidance is inadequate regarding the interpretation of various classes of ISO 9000 standard in the context of software industry, and one has to keep on cross-referencing the ISO 9003 document. Why get ISO 9000 certification? There is a mad scramble among software development organizations for obtaining ISO certification due to the benefits it offers. Let us examine some of the benefits that accrue to organizations obtaining ISO certification. ISO 9000 requires a well-documented software production process to be in place. A well-documented software production process contributes to be repeatable and higher quality of the developed software. ISO 9000 makes the development process focused, efficient, and cost-effective. ISO 9000 certification points out the weak points of an organization and recommends remedial actions. ISO 9000 sets the basic framework for the development of an optimal process and TQM. How to get ISO 9000 certification? An organization intending to obtain ISO 9000 certification applies to a ISO 9000 registrar for registration. The ISO 9000 registration process consists of the following stages. Application stage. Once an organization decides to go for ISO 9000 certification, it applies to a registrar for registration. Pre-assessment. During this stage, the registrar makes a rough assessment of the organization. Document review and adequacy audit. During this stage, the registrar reviews the documents submitted by the organization and makes suggestions for possible improvements. Compliance audit. During this stage, the registrar checks whether the suggestions made by it during review have been complied to by the organization or not. Registration. The registrar awards the ISO 9000 certificate after successful completion of all previous phases. Continued surveillance. The registrar continues monitoring the organization periodically. Limitation of ISO 9000 certification. ISO 9000 does not provide any guideline for defining an appropriate process. ISO 9000 certification process is not foolproof or no international accrediting agency exists. ISO 9000 does not automatically lead to continuous process improvement. Uses of ISO. ISO certification is used as a reference model for a contract between the external independent parties. It must be remembered that ISO certification does not guarantee a high-quality product. It focuses mainly on the processes. ISO is now being used as a standard and basis of evaluation for international bidding. ISO 9000 specifies a set of guidelines for repeatable organizations. A repeatable organization is one where the production process is person independent. ISO 9001 requirements. In this video, we are going to see about ISO 9001 requirements. The main requirements of ISO 9001 as they relate to software development are as follows. Management responsibility, quality system, contract reviews, design control, document control, purchasing, training. Quality records. Management responsibility. The management must have an effective quality policy. The responsibility and authority of all those work affects quality must be defined and documented. Quality system. A quality system must be maintained and documented. Contract reviews. Before entering into a contract, an organization must review the contract to ensure that it is understood and that the organization has the necessary capability for carrying out its obligations. Design control. The design process must be properly controlled. This includes controlling coding also. This requirement means that a good configuration control system must be in place. Design inputs must be verified as adequate. Design must be verified. Design output must be of required quality. Design changes must be controlled. Document control. There must be proper procedures for document approval, issue, and removal. Document changes must be controlled. Thus, use of some configuration management tools is necessary. Purchasing. Purchased material, including bought-in software, must be checked for conforming to requirements. Training. Training must be identified and met. Quality records. Recording the steps taken to control the quality of the process is essential in order to be able to confirm that they have actually taken place. Salient features of ISO 9001 requirements. In this video, we are going to see about salient features of ISO 9001 requirements. Salient features of ISO 9001 requirements. Document control. All documents concerned with the development of a software product should be properly managed, authorized, and controlled. This requires a configuration management system to be in place. Planning. Proper plans should be prepared and then progress against these plans should be monitored. Review. Important documents across all phases should be independently checked and reviewed for effectiveness and correctness. Testing. The product should be tested against specification. Organizational aspects. Several organizational aspects should be addressed. Benefits of the ISO 9001 standard. Enhanced customer satisfaction and improved customer loyalty leading to repeat business. Integration and alignment of internal processes which will lead to increased productivity and results. Enhanced business performance and better cost management. Providing confidence to interested parties as to the consistency, effectiveness, and efficiency of the organization. Consistency in the delivery of your product or service. Lower costs and shorter cycle times through effective use of resources. Improved communication, planning, and administration processes. Capability maturity model. In this video, we are going to see about capability maturity model. The Software Engineering Institute (SEI) has developed a comprehensive process meta model emphasizing process maturity. It is predicated on a set of system and software capabilities that should be present when organizations reach different levels of process capability and maturity. CMM is used in assessing how well an organization's processes allow to complete and manage new software projects. The CMM describes the principles and practices underlying software process maturity. It is intended to help software organizations improve the maturity of their software process in terms of an evolutionary path from ad hoc, chaotic processes to mature, disciplined software processes. 5 levels of CMM. Initial, repeatable, defined, managed. Optimizing. Initial. Few processes are defined and individual efforts are taken. Repeatable. To track cost, schedule, and functionality, basic project management processes are established. Depending on earlier successes of projects with similar applications, necessary process discipline can be repeated. Defined. The process is standardized, documented, and followed. All the projects use documented and approved version of software process, which is useful in developing and supporting software. Managed. Both the software process and product are quantitatively understood and controlled using detailed measures. Optimizing. Establish mechanisms to plan and implement change. Innovation ideas and technologies can be tested. Structure of capability maturity model. In this video, we are going to see about structure of capability maturity model. Structure of capability maturity model. Maturity level. A layered framework providing a progression to the discipline needed to engage in continuous improvement. It is important to state here that an organization develops the ability to assess the impact of a new practice, technology, or tool on their activity. Hence, it is not a matter of adapting these, rather it is a matter of determining how innovative efforts influence existing practices. Key process area. Key process area (KPA) identifies a cluster of related activities that, when performed collectively, achieve a set of goals considered important. Goals. The goals of a key process area summarize the state's that must exist for that key process area to have been implemented in an effective and lasting way. The extent to which the goals have been accomplished is an indicator of how much capability the organization has established at that maturity level. The goals signify the scope, boundaries, and intent of each key process area. Common features. Common features include practices that implement and institutionalize a key process area. These 5 types of common features include commitment to perform, ability to perform, activities performed, measurement and analysis, verifying implementation. Key practices. The key practices describe the element of infrastructure and practice that contribute most effectively to the implementation and institutionalization of the key process areas. Framework for CMM. Process definition criteria are the set of information that must be included in a software process description for it to be usable by the people performing the process. Process element answers. Purpose. Why is a process performed? Input. What work products are used? Output. What work products are produced? Role. Who performs the activities? Activity. What is done? Entry criteria. When can processes begin? Exit criteria. When can process be considered complete? Procedure. How are activities implemented? Other process elements. Reviews and audits performed. Work products that are to be managed and controlled. Measurements to be made. Training. Tools. Software Process Framework for SEI's CMM. The Software Process Framework documented is intended to guide those wishing to assess an organization or project's consistency with the CMM. For each maturity level, there are 5 checklist types. Type, description. Policy. Describes the policy contents and KPI goals recommended by the CMM. Standard. Describes the recommended content of select work products described in the CMM. Process. Describes the process information content recommended by the CMM. The process checklists are further refined into checklists for roles, entry criteria, inputs, activities, outputs. Procedure. Describes the recommended content of document procedures described in the CMM. Level overview. Provides an overview of an entire maturity level. The level overview checklists are further refined into checklists for KPI purposes, KPI goals, policies, standards. Six Sigma. In this video, we are going to see about Six Sigma. The purpose of Six Sigma is to improve processes to do things better, faster, and at lower cost. It can be used to improve every facet of business from production to human resources to order entry to technical support. Six Sigma can be used for any activities that are concerned with cost, timeless, and quality of results. Therefore, it is applicable to virtually every industry. Six Sigma at many organizations simply means striving for near perfection. Six Sigma is a disciplined data-driven approach to eliminate defects in any process from manufacturing to transactional and from product to service. The statistical representation of Six Sigma describes quantitatively how a process is performing. To achieve Six Sigma, a process must not produce more than 3.4 defects per million opportunities. Total number of Six Sigma opportunities is then the total number of chances for a defect. Process sigma can easily be calculated using a Six Sigma calculator. Statistical viewpoint. Six Sigma method has two major perspectives. The origin of Six Sigma comes from statistics and statisticians. From the statistical point of view, the term Six Sigma is defined as having less than 3.4 defects per million opportunities, or success rate of 99.997%, where sigma is a term used to represent the variation about the process average. If an organization is operating at 3 sigma level for quality control, this is interpreted as achieving a success rate of 93%. Therefore, the Six Sigma method is a very rigorous quality control concept where many organizations still performs at 3 sigma level. Business viewpoint. In the business world, Six Sigma is defined as a business strategy used to improve business profitability, to improve the effectiveness and efficiency of all operations, to meet or exceed customers' needs and expectations. The Six Sigma approach was first applied in manufacturing operations and rapidly expanded to different functional areas such as marketing, engineering, purchasing, servicing, and administrative support once organizations realized the benefits. Particularly, the widespread applications of Six Sigma were possible due to the fact that organizations were able to articulate the benefits of Six Sigma presented in financial returns by linking process improvement with cost savings. Six Sigma process and methodologies. In this video, we are going to see about Six Sigma process and methodologies. Six Sigma process. Six Sigma is a systematic data-driven approach using the define, measure, analysis, improve, and control DMAIC process and utilizing design for Six Sigma method DFSS. The fundamental principle of Six Sigma is to take an organization to an improved level of Sigma capability through the rigorous application of statistical tools and techniques. Six Sigma strategies, tools, techniques, and principles pointed out that Six Sigma is more comprehensive than prior quality initiatives such as total quality management (TQM) and continuous quality improvement (CQI). Six Sigma is equal to TQM or CQI plus stronger customer focus plus additional data analysis tools plus financial results plus project management. Use of two Six Sigma sub-methodologies. DMAIC. The Six Sigma DMAIC process, that is define, measure, analyze, improve, control, is an improvement system for existing processes falling below specification and looking for incremental improvement. It is a closed-loop process that eliminates unproductive steps, often focuses on new measurements, and applies technology for continuous improvement. DMADV. The Six Sigma DMADV process, define, measure, analyze, design, verify, is an important system used to develop new processes or products at Six Sigma quality levels. It can also be employed if a current process requires more than just incremental improvement. Both Six Sigma processes are executed by Six Sigma green belts and Six Sigma black belts and are overseen by Six Sigma master black belts. Many frameworks exist for implementing the Six Sigma methodology. Six Sigma consultants all over the world have also developed proprietary methodologies for implementing Six Sigma quality based on their similar change management philosophies and application of tools. DFSS methodology. DFSS is a systematic methodology utilizing tools, training, and measurements to enable the organization to design products and processes that meet customer expectations and can be produced at Six Sigma quality levels. The goal of DFSS is to achieve minimum defect rates, Six Sigma level, and maximize positive impact during the development stage of the products. It is used to develop new products or services with a Six Sigma criteria, capability, and performance. It utilizes a variety of quality-oriented tools and techniques to meet customer requirements and has shown an increase in lifecycle profits. DFIO and BAR EI summarize 7 elements of DFSS as follows. Drives the customer-oriented design process with Six Sigma capability. Predicts design quality at the outset. Matches top-down requirements flow with capability flow app. Integrates cross-functional design involvement. Drives quality measurement and predictability improvement in early design phases. Uses process capabilities in making final decisions. These Six Sigma elements can be arranged in a framework by the proposed mediation model. The figure shown leadership as a driver of 3 other elements, and it is an exogenous variable as is commonly proposed in the literature. Leadership should lead to strategic project selection and the use of improvement specialists. These 2 elements in turn enable the use of the structured method for process improvement. Finally, the structured method leads directly to improved organization performance. Six Sigma and productivity. The program is designed for quality service managers and administrative or professional staff who are seeking to learn and apply Six Sigma language and concept at their respective workplaces. Training objectives. How Six Sigma can perfect processes and drive down costs. How to apply Six Sigma methodologies for improving an existing process to Six Sigma level. How to apply Six Sigma frameworks on an improvement project. Six Sigma tools and techniques. How to analyze data using simple Six Sigma tools. Learning outcomes. The program will be taught by staff of Office of Quality Management. Methodologies used include action learning, experiential learning, case studies, experience sharing, and group discussions. The training sessions are intended to be hands-on and practice-oriented. Overview of Six Sigma. What is Six Sigma? Concept of Six Sigma. Core principles and benefits of Six Sigma. Setting business metrics. Cost of poor quality. Six Sigma methodology. The DMA IIC roadmap. Define, measure, analyze, improve, implement, control. Project selection and initiation. Project selection. Reinformation of facilitation. Project charter. Deployment of Six Sigma. Leadership. Quality service culture. Roles and responsibilities. Debrief and program review. All participants will be asked to utilize the DMAIIC method to analyze problem in their organizational unit. A program review will be held at the end of the program to gauge the effectiveness of the training program. Duration or date. The program will be conducted twice a year. Uses of Six Sigma. Many companies today use Six Sigma, a set of tools and procedures developed by Motorola, which aims to improve business processes. Any good company that produces a product or service uses the Six Sigma quality control strategy to ensure great customer service and product reviews.